I see. Yeah, actually, this project that I'll be talking about, this paper, it was the first project really that I was involved with after finishing the PhD, but we only finished actually writing it this year, and so now I think it's a good time to talk about it. Okay, so it's going to be a talk about graph minors. So what's a graph minor? I'm sure you've all seen before, but a graph H is a minor of a graph G if we can obtain H from G by deleting vertices, deleting edges, and then this operation of an edge contraction. Right, so here we contract these two adjacent vertices into a single vertex, which is then adjacent to all of the neighbors of the two contracted vertices. So this is the operation of contracting an edge. So here's a picture, right? So if we start with the graph, this complete multipartite graph K22222, we can contract this red edge here down to this red vertex, and this blue edge here down to this blue vertex to obtain this graph K8 minus 1 edge. And then by deleting one vertex, we can contain K7. This is kind of an interesting case. This graph contains K7 as a minor, but it doesn't contain K8 as a minor. And it's actually the unique densest graph on 10 vertices which does not contain K8 as a minor. But there's another way of talking about graph minors. So instead of talking about this sequence of operations, we can just look at this graph here and say that, well, in this graph, we can represent every vertex of K7 with a connected subgraph. So that, so we call this a model of the graph H. And the conditions are that, so each vertex of H is mapped to some set of vertices from the graph G, so that each of these sets is a connected subgraph. And whenever a pair of vertices in H are adjacent, then the sets of vertices in G are adjacent. And of course, we want these to be disjoint. Okay, so this is an equivalent definition of a graph minor. And yeah, I guess one of the very interesting things about graph minors that sort of obligatory to mention in any graph minor talk is this very nice theorem that every minor closed class, so every class of graphs that's closed under the operation of taking minors, can be precisely characterized by listing a finite set of graphs which are excluded minors for the class. And there's of course lots of interesting examples of minor closed classes. So like planar graphs is one of the famous examples where we actually know the excluded minors are K3 and K5. But any class of graphs defined by embedding on the surface is closed under taking minors, and there are many other classes. An interesting one for this that will sort of come up later maybe is if you just take any graph, so take the class of graphs with bounded component size, for example. So components of size at most k, of course, this is a class of graphs which is closed under taking minors. Okay, so the question we're going to be interested in for this talk is what can we say about the density of graphs not containing a particular graph H as a minor? So here we define the density just to be the ratio of the number of edges to the number of vertices. And yeah, so we define this extremal function as the supremum of the densities of graphs G such that H is not a minor of the graph G. Okay. So this is quite a well-studied thing. So in the case of complete graphs, there's been particularly quite a lot of research. So we know precisely not only this extremal function, but also the precise maximum number of edges that you can have in an n-vertex graph, not containing a complete graph H for all of the small complete graphs up to K9. I believe I believe K9 is still the state of the art, although there is, I believe, some people working on K10 at the moment. Yeah, so we see for all of these ones, this extremal function, so for K3, the extremal function is just 1, and this is just, so the graphs excluding K3 are just forests, of course. Then for K4, the extremal function is 2, and there's this nice pattern that you might observe over here, which completely breaks down when you take the limit. So when you look at large complete graphs, actually the extremal function is actually not a linear function of t. So this, the order of magnitude of this was independently determined by Kostochka and Thomason. And Thomason actually determined precisely this constant alpha in this extremal function here. And the construction here is basically you just consider random graphs, but you carefully pick the right density for the random graphs and the right size for the random graphs, so that you get the right extremal function. And then you could just take disjoint unions of those to get arbitrarily large graphs of that density. Okay, so the result for general complete graphs was sort of extended to non-complete graphs. So there's this formula here, which sort of asymptotically determines the extremal function for graphs which are polynomially dense. So we say that a graph is polynomially dense if for some constant tau, the number of edges is n to the power, or t to the power of 1 plus tau for for a t-vertex graph. So this theorem sort of gives a formula for the extremal function of almost all graphs. But the interesting thing to note here is that this formula doesn't really say anything for graphs which are not polynomially dense. So, for example, if you consider a class of graphs where this density is bounded by a constant, then this formula doesn't give you any real information about the extremal function for graphs from that class. And interestingly, so what's an example of a class of graphs where the density is bounded by a constant? Well, sort of, it follows from the previous slide actually that any minor closed class, any proper minor closed class, will have density bounded by a constant if you exclude any graph at all. Okay, so we're going to be interested in analyzing the extremal function for sparse classes of graphs. And in particular, what I mean when I talk about a sparse class of graphs for the purpose of this talk is a class of graph which admits strongly sublinear separators. So we say that class F admits strongly sublinear separators. Firstly, if F is closed under taking subgraphs, that's important. But also, there needs to be constants beta strictly less than 1, and some some positive constant c, such that every graph from the class has what's called a balanced separator of low order. So what is a balanced separator? So we want to separate the graph into two subgraphs H1 and H2, so that their union is the entire graph. And we want this to be a balanced separator, so we want that neither of these graphs is too small. And then the order of the separator is the size of the intersection of these two graphs. And here is where this strongly sublinear condition comes in. So the size of the intersection should be at most some constant times the number of vertices to the power of beta. Okay, so if F satisfies these conditions, we say that F is strongly sublinearly separable, or just SSS. And we'll note that every proper minor closed class is SSS. If you're familiar with polynomially bounded expansion, then that's another way of talking about it. It's basically the same as having polynomially bounded expansion. But I won't explain what that is. Okay. Okay, so unbeknownst to us when we started working on this, so that there is now this result of Haslegrave, Kim, and Lee, which has made a lot of progress on computing extremal functions for sparse minors in exactly the same sense that we were interested in. So they found this bound, which is very good. This, so the extremal function of a graph H from an SSS I'll just call it a sparse family F, is bounded above by something which is almost the number of vertices minus this constant here. So here, alpha 2 is the largest bipartite subgraph, the size of the largest bipartite subgraph. So in general, we'll write alpha k to mean the size of the largest k-colorable subgraph. Induced subgraph, sorry, that's important, otherwise you could take hold. So yeah, or you could think of it as the union of two independent sets. But in terms of that function there, they get this bound on the extremal function for graphs from a minor closed class. And if you consider this sort of meta-extremal function, which asks for the maximum value of all of the extremal functions sampled from T vertex graphs from a particular sparse class of graphs, then they get this nice result for any fixed surface. If you consider the class of graphs embeddable on that surface, then the maximum value that this extremal function will take is about 3t on 2. And yeah, this is tight. Okay, so these are our main results. So for every sparse class of graphs and every 4-colorable graph from the class, we get this more or less precise calculation of the extremal function of this graph. So it's the maximum of either the number of vertices divided by 2, or the number of vertices minus the size of the largest independent set. So I guess this is equivalent to the size of the smallest vertex cover. And sort of as a corollary of this, we get a bound of this form for removing this chromatic number condition. We get a slightly less precise bound, but here we get the number of vertices minus the size of half the size of the largest 3 chromatic induced subgraph, or this same parameter here. So if we compare this to the previous result, this is a slight improvement, very slight improvement on this here. So we basically replace alpha 2 with alpha 3, but then when you do that replacement, you also need to consider this, that this term may now be bigger. Okay. But I should mention that this paper also has some very nice results about subdivisions, which I won't talk about because we don't do anything for subdivisions. But really, it's the techniques in this paper are completely different from the techniques that we use. It's basically sort of doing very similar things in very different ways. Okay, so we have another result. So if you have a sparse class of graphs, and we have this parameter here, which looks at the largest ratio of this size of the smallest vertex cover divided by the number of vertices for every graph H such that disjoint unions of H are still in the class. So if you have a class of graphs which is closed undertaking disjoint unions, you can just ignore this condition that KH is in F for all K and N. But for technical reasons, we need to include it if we want to talk about all sparse classes. So if this parameter is at least 2/3, then this gives an upper bound for the extremal function for graphs from this sparse family, and it is a tight upper bound. So there also exist arbitrarily large graphs where this is the actual size of the extremal function. Okay. So I'm actually not going to talk very much about any of that. Instead, what I want to focus most of this talk on is the fractional extremal function. So this fractional extremal function I'll quickly define. So the fractional extremal function for a graph H is just the limit as k goes to infinity of the extremal function of k disjoint copies of H divided by k. Okay. So this has some nice properties. So it has the property that if you multiply the extremal function by L, it's the same as taking the fractional extremal function of L copies of H. And also has this nice property, of course, if you delete a vertex, the fractional extremal function doesn't increase, but it also doesn't decrease by very much. So we get this nice bound here. But the main reason that this function turns out to be interesting is that for every sparse family and every graph in that family, the extremal function is actually almost equal to the fractional extremal function. So this is the motivation for introducing this new parameter, and it is also through studying this parameter that we obtain sort of the results of the paper, the main results of the paper. Okay, so the main thing I want to talk about actually is this result, that we can approximate with the extremal function with the fractional extremal function. But first, I want to talk a bit more about what exactly this fractional extremal function is. So to do this, let me introduce a jumbled model of a graph. So here again is the definition of a model of a graph. A jumbled model is just a model where we forget about this condition that the bags corresponding to the vertices should be disjoint from each other. So instead of forcing these bags to be disjoint, all we're going to do is we're going to record for each vertex of G how many bags contain that vertex. So we just keep track of how badly we went wrong in constructing the minor, basically. And so one thing to observe is that if this discrepancy is less than k for all vertices of the graph G, then H is actually a minor of this blow-up. So if we replace every vertex of G with an independent set of size k, then we can just take different copies from the independent set to the different bags, and we'll actually find a model which is not jumbled anymore. That's just an observation. It's, yeah. Okay, so the reason for introducing these jumbled models is that so I can talk about the H volume of a graph. So we'll say a fractional packing of jumbled models is just a collection of jumbled models together with some vector of weights, so that so now the weight of the packing is just the sum of the weights of the jumbled models, the sum of the weights of the jumbled models, and then the restriction is that the total weight of this sort of overlap at each vertex should be bounded by 1. And then, so this is sort of, yeah. sort of a fractional relaxation of finding a minor now. So we define the H volume of a graph G to be the maximum weight of a fractional packing of jumbled models of H in G. And there's a couple of things to note. First, if H is actually a minor of G, then, well, in particular, we have a model which is not jumbled, and we can just assign weight 1 to that model to show that the H volume of G is at least 1. But similarly, if K times H is a minor of the Kth blow-up of G, then the H volume of G will also be 1, or will also be at least 1. This is not as immediate to see, but basically it's the same idea, that we just take different, so if we take the Kth blow-up, then suddenly all these sort of overlapping vertices can be just, sorry, no, going the other way, yeah, right. Yeah, it goes in the other direction. So if you're a minor, if K times H is a minor of the Kth blow-up of G, then we can sort of think of each copy of K times H as a jumbled model inside the graph G itself, and the inequalities will work out. Yeah, right. So a jumbled model again. So all it is, so each vertex of H is mapped to a set of vertices from G, so that each set induces a connected subgraph, and each pair of vertices which are adjacent in H are mapped to adjacent vertices in G. And so we forget about condition 3 for the jumbled model, but instead we look at each vertex, how many times is that vertex used for every vertex in G. So then when we do the fractional packing, the total number of times that each vertex will be used among all of the jumbled models in the packing should be at most 1. Okay, so maybe I give a quick example of why. So what's an example of a graph where the H volume is at least 1, but the graph does not contain a copy of H? So actually, so if you consider this graph here, and H just the graph C4, then of course H is not a minor of G. However, so if this is vertex A, B, C, D, then we can find a jumbled model by mapping A and C to this vertex, and B and D to this vertex. So now there's an edge between A and B and C and D and D and A. So it preserves property 2. Let me go to here. It preserves property 2. But if we assign this jumbled model weight half, then the total weight at each vertex will only be 1. And then we get a second jumbled model over here by doing the same thing. So we get 2 jumbled models, each of weight half, that we can pack into the graph, and therefore the sum of the weights of the jumbled models is 1. So this means the H volume of G is greater than or equal to 1. But another way of seeing this, which I talk about here, is if we take take a blow up of G, so we place each vertex of G with an independent set of size 2, then you obtain this graph here, and we see that 2 disjoint copies of H are now just occur as minors of this graph. So, yeah, 2H is a minor of G to the 2. So this is another way of seeing that the H volume of G is at least 1 for this graph here. Okay. And so with this definition, we can now yes, right. We now get this result, this equivalent definition of the fractional extremal function. So the fractional extremal function of a graph H is just the supremum of the density of G divided by the H volume of G over all graphs G. Now, it's not immediately obvious, of course, that this is an equivalent definition, but it turns out to be an equivalent definition. So if you think of, so if the H volume is strictly less than 1, then what we know is that the kth blow up of G does not contain KH for any value of K. So if we put this just less than 1, then we're looking at the supremum of graphs G where this H volume is strictly less than 1. So it's sort of makes sense, but it's a bit yeah, it's not clear that you would get the equality, but you end up getting that these are precisely equivalent. Okay, so now I want to take a slight diversion and ask, how do we construct lower bounds for this extremal function or for this fractional extremal function? So the first thing, since this is true, we can actually see, it comes from the first definition that the fractional extremal function is a lower bound for the extremal function. Yeah, anyway. Okay, so let's look at this graph again, because this, as I mentioned, this graph here is the densest 10-vertex graph, which does not contain K8 as a minor. So if we can understand why this graph doesn't contain this graph as a minor, and we can generalize this construction, maybe we can get a nice construction in general for a dense graph which does not contain a particular graph H as a minor. Motivated by this, here's a question. What is the smallest k-part 8 graph which contains H as a minor for any graph H? So we can actually answer this question. So if H is a minor of G and G is bipartite, then the number of vertices of G should be at least the size, this function alpha R of H. So this is the size of the largest R-partite induced subgraph of H, plus 2 times the remaining vertices of H. And the reason for this is that so if you find a model of a graph H in a graph G, then all of the bags which have size 1 should just correspond to a subgraph of H which is also a subgraph of G. You don't get extra edges between those vertices, which get bags of size 1. So almost all of the bags should have size 2. Only this many vertices can get bags of size 1, which means the total number of vertices of G should be the sum of all the sizes of the bags, which ends up being this constant here. So if we consider the graph K8, then the largest 5-partite subgraph of K8 is of course K5. So the largest subgraph of K8, which is also a subgraph of K2222, has 5 vertices. Now, if we want to build the 6th vertex of K8, we would need to contract a pair of vertices. And if we want to build the 7th vertex of K8, we would need to contract another pair of vertices. And if we want to contract the 8th vertex of K8, we would need to contract 3 pairs of vertices and then leave 5 vertices uncontracted. But this graph here, you can't contract 3 pairs of vertices and leave 5 vertices uncontracted because there's just not enough vertices. So that's where this formula comes from. And using this formula, we can get this lower bound here. So if we consider a Turan graph, so a balanced complete multipartite graph with R parts, then if the number of vertices is just less than k times this function here, then it has no kh minor. So here we're using that both the number of vertices and this function alpha r of h scale linearly if we take k copies of h. But yeah, this function here is just the density of the Turan graph divided by k, if you take the limit. And so the other lower bound we get is by considering a complete unbalanced bipartite graph. Then in this case, if one side of the bipartite graph has just fewer than this many vertices, then the bipartite graph will not contain a graph H as a minor. So we can get a lower bound this way as well. And these are basically the best lower bounds we know for the general problem. And they are lower bounds for the fractional extremal function, but the fractional extremal function is itself a lower bound for the extremal function always. Okay. So now I want to talk about this result. So from the definition, it follows that the fractional extremal function is bounded above by the extremal function. So what we want to show is that the extremal function is also bounded above by something which is approximately the fractional extremal function. So the strategy for proving this goes something like this. So first, since f is from some class which admits strongly sublinear separators, it turns out that a large graph selected from f looks kind of like a disjoint union of copies of some small graph. So I'll explain later what exactly I mean by this. It's kind of a surprising result when you first see it, maybe. But in particular, it's a close enough approximation that the fractional extremal function for h will be approximately equal to the fractional extremal function of L copies of this small graph, which in turn is equal to L times the fractional extremal function of the small graph. Okay, so now if we have some graph whose density is at least this, this value here, then, well, in particular, the number of vertices should also be at least this number here, which means that G is quite large. And if G is quite large, then it kind of looks like a blow-up of a smaller graph. So this is basically the regularity lemma. And in particular, the K, so K times the H volume of R will be greater than or equal to this coefficient L. And we will see that this expression here allows us to find L times G as a minor of G. And, well, this graph that we find as a minor looks like the graph that we're looking for. So, done. This is not quite the end of the proof, but this is the first goal, to get to this point here, where we get something which is, I promise, almost the thing we're looking for. So this is what I mean when I say that for a large graph from an SSS class, it looks like the disjoint union of a copies of some small graph. So for every positive epsilon, there exists some constant C. Now, this constant, this is a very large constant, but it is just dependent on epsilon and the class. But every graph H from F, there exists some graph H prime, which contains H as a minor. So that's a good first step. That means that if we contain H prime as a minor, we contain H as a minor. And there's some small set of edges. So here small, less than epsilon times the number of vertices of H. And if you delete these edges, then what's left is just the graph L times J for some graph J which is small, so bounded by this constant C. And finally, there's some small set of vertices, so that if you delete these vertices, then you're left with a subgraph of H. So H is sort of quite close to this graph here, if we are allowed to ignore some small set of edges and some small set of vertices. Yeah, and this, all we need for this is this, the strongly sublinear separators. And this is basically where we use the fact that we're working with a sparse class of graphs. Now, maybe the most surprising thing about this result, if you're familiar with these sparse classes of graphs, is that we only need one graph J. This would perhaps look less surprising if I just said that, well, we can approximate the graph by splitting it into components of some bounded size, and we only need to delete some kind of small set of edges to do this. But it turns out that that's not really a big distinction, because we can just group small components together. If you have lots and lots of small components, you can group them into large collections of components, so that all of the collections look exactly the same, because there really just aren't many graphs which are small. So that's a very rough explanation of what's going on, and it sort of might give you some idea of how large this constant C is. So in particular, in this situation, since we have this nice property of the fractional extremal function, that when you delete one vertex, you decrease the function by at most one, we're only deleting a small set of vertices. So we do get that the extremal function for H is approximately equal to the extremal function of this graph formed by L disjoint copies of J. Okay. So roughly that's the first step. The second step, as I mentioned, is some version of the regularity lemma. It's perhaps not the most common formulation of the regularity lemma. So what we will say is that if we have so for every epsilon, there exists some t, such that for every k, there exists some n. And now whenever we take a graph which is sufficiently large, so larger than n, there is some graph R such that G looks like the kth blow-up of R, if you squint at it. So what does that mean? So firstly, k times the number of vertices of R should be approximately equal to the number of vertices of G. So bounded above by the number of vertices and bounded below by something close to the number of vertices. And then we get this expression here that k squared times the number of edges of R should be at least something close to the number of vertices of G, so minus a small amount. And when I say that G looks like the kth blow-up of the graph R, what I mean is that if we have some graph which is a subgraph of this kth blow-up of R, and every component of this graph is small, then it's also a subgraph of G. So if we're only looking at subgraphs which have small component size, then all of the subgraphs satisfying that condition for the kth blow-up of R are also subgraphs of G. So that's nice. And so this second condition basically guarantees that the density of the kth blow-up of R is approximately equal to the density of G. And that's why we need the second condition. Okay. So the reason it's nice to consider the kth blow-up of a graph is for this reason here. So for every positive t, there exists some positive k such that if you have two small graphs, so v of h and v of g are both bounded by t, then we get sort of what you would expect here. That if you have some L which is less than or equal to k times the h volume of G minus some negligible amount, then H is a minor of the kth blow-up of G. So combining this with the previous version of the regularity lemma, the reason that this is useful is that we get something like the following. So this one might make more sense. For every epsilon and every graph H, there exists some constant L, such that if lowercase l is sufficiently large now, and the density of G is at least L times the fractional extremal function of H plus some small amount, then L times the graph L disjoint copies of H is a minor of G. Okay, so if you believe this, you can sort of forget about the previous things. This is why we care. Right, so this is looking pretty good. So at this point, we can decompose our graph H so that it looks like L copies of some graph J, where J is small. And then we assume that the density of a graph G is at least the fractional density, maybe plus a little bit, of the graph H, which is approximately equal to the fractional density of L times J. And therefore, we do find L times J as a minor of G. However, that's not actually quite enough anymore. So if we look at this, so this what we actually find here is that we get L times J as a minor of G, but we need actually to find H as a minor of G, or maybe H prime. But we are only missing a very small number of edges. So basically, if we can somehow add these extra edges back in, then we will be done. So what we need to do is somehow connect these disjoint copies together with these extra edges that we've thrown away. So the way we do this, okay, I should probably start going a bit quicker. Right, yes, here. Sorry. Oh, I'm going backwards. That was confusing. Okay, sorry. Okay, so here is the next lemma that we're going to need. So this lemma says, basically, that if you have any graph at all, then you can find a minor of this graph, which almost has the same density that you started with. So this minor has some connectivity, some linear connectivity. But also it almost has the same density as you started with, unless this condition here holds. So either the number of vertices is some large amount and the minimum degree is some large amount, or the density of this graph hasn't really changed much at all. So the idea for proving this is to first contract any edge of G which is in a small number of triangles. Here small means at most D. So when you contract an edge which is in at most D triangles, what will happen is that the number of vertices will reduce by 1, and the number of edges will reduce by most D. And this is exactly the ratio to preserve the edge density of the graph. So we can do this as many times as we like, and we will still have a graph with at least the same density as before. And at the end of this process, we will have a graph where every edge is in at least D triangles, which is quite nice, because that graph has minimum degree at least D as well. Now, because the minimum degree of this graph is so high, if the number of vertices is small at this point, then the connectivity is already high, and we don't need to do any more. That's all we needed. But in the second case, where the number of vertices is now too big for this argument to work, we will have to instead combine some neighborhoods of small degree vertices, and we can combine them together so that they, instead of satisfying this condition 2, will instead satisfy condition 1. But don't worry about that, because we'll just ignore that from now on. Okay. Right. So the takeaway from this lemma, if we ignore the second condition, is that we can, without decreasing the density, so if we ignore condition 1, then without decreasing the density much at all, we actually get some positive connectivity. And if you have some small connectivity, this allows you to find some small set of vertices such that whenever you take a very small number of pairs of vertices, then you can link those vertices together in pairs so that all of the internal vertices of all of the paths in the linkage are in the set Z. So the reason that this lemma is good is now we can delete this set Z to begin with. And then if we find the minor of, then if we find a copy of L times J as a minor from before, remember we just had to add a small number of edges back. And this set Z is exactly what we need to have set aside so that we can add those edges back in. So I won't really go into the proof here, but basically it turns out that you can just randomly select this set Z and it will work out. Because the connectivity is so big, between any pair of points, there are lots and lots of paths between those points, and lots of disjoint paths, which means a lot of those paths are very short. And if those paths are very short, then some positive fraction of those will likely be contained in a random set. So it's not a difficult proof. It's just basically some probabilistic stuff. But I won't go into the details. So now the strategy actually works if we set aside some set of vertices like this. So as before, we decompose the graph H. But now we're going to assume that we can find a minor G prime of this graph G. And G prime is highly connected, but still has about the same density. And now we set aside some set of vertices Z, and this graph G prime after we set these vertices aside, still has high density. And as before, now G prime will contain L copies of this small graph H as a minor, but now now this set Z will allow us to actually find the graph H as a minor. Okay. Yeah. So sorry, that was a bit rushed maybe, but that's the overall basic strategy of the proof, if you omit the more interesting case. Okay, so now let me try and quickly give some explanation why we actually care about this, why it's a good thing that we can look at the fractional extremal function instead of the extremal function. So to do this, I want to consider weighted graphs. So a weighted graph, we just assign some weight to each vertex. And you can sort of think of these weights as corresponding to some blow up of a graph. So like if we assign each vertex weight 2, then it's like we're taking this 2 blow up, we're blowing up each vertex with an independent set of size 2. Now, we define the density of the weighted graph so that it basically equals the density of that blow up. So it's just, so yeah, the edge weight should be the products, each edge has the weight equal to the product of the weights of the vertices, and then you sum them together to get the total edge weight of the weighted graph, and then the density of the weighted graph is the total edge weight divided by the total vertex weight. And we can define a jumbled model for weighted graphs in a very similar way to the way that we define them for graphs. But now instead of, so previously this condition was that for every vertex, the total overlap multiplied by the weights of the jumbled models was bounded by 1. Now we bound it by the weight of the vertex instead. And this gives us, essentially this gives us yet another way of defining the fractional extremal function, because we can actually define the fractional extremal function in terms of weighted graphs. What we find is that the fractional extremal function is the supremum of the density of a weighted graph divided by the H volume of a weighted graph. But now we can rewrite this as the supremum of the density of a weighted graph under the condition that the H volume of the weighted graph is strictly less than 1. So these end up being equivalent here. And this is easier now because basically the weight function allows us to do linear scaling. So what we can do is we can always pick a weighted graph where the H volume has any fixed value we like by just scaling the weight function. So if you scale the weight function, it will also linearly scale the H volume of the graph. So and it linearly, so both the density and the H volume of any graph are sort of linear in this weight function. So that's why we are allowed to go from this step here to this step here. And so this version here looks kind of similar to, looks a bit more similar to, this version looks a bit more similar to the definition of the classical extremal function. But what's really nice is that we can actually go one step further. And when we consider weighted graphs, we only actually need to consider weighted cliques. I guess I should finish about now, so I won't actually go through this proof, but it's not actually very difficult. But the point of replacing weighted graphs with weighted cliques is that now we don't actually care about the structure of the graph G when we consider the weighted graph GW. So instead of considering this weighted clique with drawn here, we can just consider basically some vector of weights, because we know the graph structure is always going to be a clique for every graph we care about. So in summary, basically everything up to this point has been justifying that studying extremal functions for sparse minors is basically a problem in linear algebra. Okay, so that's the end of my talk. Thank you.
Any questions?
So in the regularity lemma, what's the gap between the capital K and N?
In the regularity, what's the gap between, sorry, what's the question? Yep. Oh, I don't think, yeah, I mean, I don't know what it is. Yeah, I would guess it's very big. I don't know if that's the worst. Like we don't really make any effort to optimize the lower order terms in anything that we do in this paper. I'm not sure if this is the worst contributor, but probably one of the big contributors.
Shallow D minus, and there is also a similar concept to jumbled minors called congested minors. I think that's nothing but a shallow D jumbled minors. So we may define similar fractional packing number. So my question is that do you believe that the similar ideas work for that shallow D minors?
Shallow D minors. Yes, I expect so because. Well, basically, if we go to the very last slide, the sort of takeaway from this is that we expect the extremal graphs to basically look like complete multipartite graphs. And in complete multipartite graphs, all minors are shallow, in the sense that whenever you contract a pair of vertices, you already create a dominant vertex. So if H is a minor of a complete multipartite graph, and H is a shallow minor of a complete multipartite graph. So that's why I'm not sure. So maybe, yeah, maybe. At least that's my gut reaction is that it should then be possible.
Is there a version for Pruska line?
Oh, so so our techniques don't really work for topological minors. But I should advertise again this previous paper, which does talk about topological minors quite a bit and get some very nice results. So I got, I believe, extremal density for sparse minors and subdivisions. I think that's the title. I don't think. Our techniques don't really give any easy way of applying to topological minors.
There's a question from Tony. Do you think your results hold for bounded extension graph classes?
Just without polynomially bounded, just bounded expansion. We do talk a little bit about some stuff beyond polynomially bounded classes. So we get similar results, for example, for hypercubes. Maybe I'm not sure. I think probably. I mean, with all of this, I think Sergey is probably going to be a better person to ask than I am. But I don't know. Possibly.
So there is this